Okay, so let me thank the organizer and the Newton Institute for this occasion to speak again. So what I will talk about will be well, what I will do. Maybe I'm using this in the wrong way. It was working. Okay, now now it works. So what I want to talk about is first introduction on what are these logarithm laws and the relation with some other feature of dynamics, namely mainly decay of correlation, and I will also speak about something about arithmetical properties. And then I want to describe in some more detailed recent result on Lorenz-like flow, where we have to study the decay of correlation of let's say a quite complex system. So let's say non-trivial construction was necessary. And let me introduce all the people with whom I learn the things I will talk about. Claudio Bonanno, Stefano Isola, Donghan Kim, Pietro Peterlongo, Zezé Pacifico, Isaia Nisoli, Vittorio Araújo, Benoît Sossol, and Jérôme Rousseau. More or less all the results I will describe will have been done in collaboration with them or by other people like this. So let me start with two old results which look quite different at the first view, but we will see that they are connected to the same idea and the same point of view, which then we will develop. So let us consider an old result, which now maybe it looks like quite trivial from the thing we know about statistics and extreme value and so on. Let us consider coin tossing, and let us consider, after tossing n time a coin, what is the longest run of head we have seen after n tossing. So this is a kind of extreme value question. For example, if you here suppose 1 is head and 0 is tail, if you toss the coin, and this is a realization of your process. For example, after 2 tossing, you have only one head. After 10 tossing, you have these 3 head, consecutive head, which gives you the longest run you have seen until now, until this tossing. The result says that the longest run of head that you see tossing the coin grows logarithmically in the number of tossing. And for example, and there is a constant which is given by the probability of head, but let's consider fair coin tossing, and so the number of consecutive heads grows really like the logarithm of the number of tossing. So this is a extreme value result, which then was generalized in many ways, and it is also, as far as I know, these results of this kind are still used in data compression theory, because you have to know when a given string will appear again in the future. So this is a result about coin tossing. Now let's go to a completely different environment and consider geodesic flow. Let us take the hyperbolic space with dimension b plus 1 and quotient with a discrete subgroup of isometry in a way that the resulting space is not compact and has a finite value, and then consider the geodesic flow on this space. This will be a constant and negative curvature space, and then consider a starting point and a geodesic which starts from the point and then go around on this hyperbolic space. You can ask yourself, since there are these gasps going to the infinite, you can ask yourself what is the speed of going to infinity, what is the longest excursion in the cusp you make after time t, and again you can prove that this goes logarithmically with the time, with a coefficient that depends from the dimension. That was a result by Sullivan in '82. And this will be for almost all the geodesics. So, but these are two results that in some sense they are related to extreme. Let us consider another more general point of view which will be applied on this problem. Let us now in general consider a metric space and an ergodic dynamic on the space. Let us consider, let's say, a typical orbit and a set that for us will be a target. And our question will be, how many iterations we need to hit the target? And then, okay, this will be something that, well, this is a general question. Then let us suppose to do it for smaller and smaller target. So what happens is that if you take a certain orbit and then you decrease the targets, then the time you need to enter for the first time in the smaller and smaller target will increase. And you want to understand how fast this time increase while you decrease the target. If the system is chaotic, mixing in some sense, we will precise then in which sense we are interested to see, but a first intuition could be, if the system is chaotic, the trajectory is like a point chosen at more or less at random in the space, and so in some sense the time you need to enter in a small target will be in some sense proportional or asymptotically. It will go like the inverse of the measure of the target. This is also confirmed if you think that to enter in the target you have to enter in the target after n iteration. It means that you are in the nth preimage of the target. If the system is mixing, probably this preimage will be mixed around the space. The geometry of the target will be not so important because it will be lost while iterating and while mixing. And so what remains, if the measure is preserved, the only information that remains will be the measure, and so you can expect something like this. The two results I was telling before indeed say something like this, because if you consider coin tossing, it's well known that you can consider it like a Bernoulli shift, so it's a dynamical system on a metric space. There is a particular point, which is the string containing all ones. The longest run of head in this dynamical system corresponds to the nearest distance that you have seen after n iteration, the nearest distance you see from your orbit, from the orbit to this particular target point, which is the string containing all one. And so the problem having the longest run of head is the same thing like asking how much time I need to hit a certain cylinder centered in this point. The measure of cylinder decreases exponentially. And so if you think like this, okay, the measure of the cylinder decreases exponentially, the time I will need to hit a given cylinder will go like the inverse of the measure. So it will increase exponentially. And so the logarithmic increase of the distance is justified by this. If you go at a certain distance, you need exponential time. It means that you go logarithmically fast with respect to the distance. And in the geodesic flow problem, the situation is analogous because you have the flow is on the unit tangent bundle. And what you want is to hit a certain sequence of target, which is the point of the unit tangent bundle whose projection is far enough from the starting point. So it's a sequence of sets who lives in the cusps, let's say. And if you compute the measure of this set, this measure decreases exponentially in the distance. And so you have the same situation. So that's why the two results look different, but they can be seen as similar answer to the same question. And now let us face the question, the general question, more systematically, giving some precise definition. So now what I understand is that I want to quantify, I have starting point and sequence of decreasing targets, and I want to quantify how much iteration I need to hit the end target. For simplicity, let's start with balls, targets which are balls. But we will see that the result more or less can be generalized to many sequence of targets. But by simplicity, for simplicity, let's start with balls. So we define this time that you need starting from it, Ex, to go to the target, near to the target point x naught at a distance less than r, okay? Let us consider this. And now we want to, what we want to look at is, okay, when you decrease r, this time will increase. Let's suppose it will increase like a power law, and let us extract the exponent. So what we do to extract the exponent, we take the ratio of the logarithm of the time divided by minus logarithm of r. But for this is something in general. Let us consider a metric space. Let's say a metric space, so you can define balls. You can define balls. And, well, of course, the first thing, if you want almost everywhere results, first thing you would like to have is that almost each point go near your target. So maybe you can ask that also that the system is ergodic, because then if there are two different ergodic components, you cannot go from the other one to the other. But let's say an ergodic dynamic touch system will have a measure which is preserved, and the space is a metric space. So we can define what is a ball. So I said we want to extract the exponent, so we take this ratio of logarithms, and so by taking the Linsup of the limit, we get two indicators, which are two estimation for the exponent of this power law. Since we want to compare with the measure, we do the same thing to the measure. We consider the limit for r going to 0 of the ratio of the logarithm of the measure divided by the logarithm of the radius. What is this? Is the local dimension, is the well-known local dimension of the measure at a given point. And again, this means that the measure goes like r to some exponent. So when the time goes like the inverse of the measure, you will have the equality of the indicator for the heating time and the local dimension. So you will have this equation, and when this happens, I will say this is a logarithm law. A logarithm law was proved for this system. What we will see is that this happened for fastly mixing system, namely super polynomially mixing system, but there are, we'll see some statement about all this, but the philosophy is that this happened necessarily for fastly mixing system. But there are mixing systems which not satisfy this, and time permitting we will discuss the case of Lorenz-like flow. But first, let me say something, because we have seen that this time question is related to the distance question, and there are, in the literature, many people face this problem from different point of view, but there are many point of view that are equivalent in some sense, and sometimes people do not notice that, that there are some duplication of results. So let me say that if you, so now we consider these heating time indicators, but we could also consider how fast the distance from the target go to 0. And these are two equivalent point of view. If you define this dn, which is the smallest distance that you have seen after n iteration in your dynamic, the indicator of heating time is will be the inverse of this indicator of how this distance decreases to 0, and sometimes similar results are also stated like this. They consider the limit of some function that multiplies the distance that you see, and sometime, and there is another branch of results that are very strongly related with the logarithm law, with the behavior of this number, which are the so-called Borel-Cantelli lemmas. Now I have no time to define, but let me just say that the logarithm law is almost the same thing as the dynamical Borel-Cantelli lemma. But maybe if there is time, maybe I will, or if someone is interested, I will explain the small difference that you can find, but these are two very strongly related. So logarithm law, strong Borel-Cantelli lemma, shrinking targets, and all these kind of things are strictly related, and you will find that many results can be translated directly from a language to another. While if someone of you is interested in distribution of heating or return time, this is a slightly stronger question. So this is anyhow. Let's come back to the logarithm law, and let us see some precise statement, general statement about this this question. So we say the logarithm law is when here there is equality, but first remark that is really a easy consequence of the easy Borel-Cantelli statement is that the heating time indicator can only be larger than the local dimension. You cannot this is, if the measure is preserved, so in very general case, you will have always this inequality. So the next question is, can we have system where this is strictly bigger than this? Yes. Can it happen for chaotic system? To answer precisely to the question, we have to look at how chaotic is the system. A way to measure this chaoticity is the decay of correlation. And here there is a definition of the kind of decay of correlation I will use. I will use decay of correlation with respect to Lipschitz observable, so they are quite regular observable. I will say that a system has superpolynomial decay of correlation with respect to Lipschitz observable if the correlation integral is bounded by the Lipschitz norm of the observable times a function which decreases in time faster than any power law. So this is a decay of correlation which is between polynomial and exponential. So it is faster than any power law. This is enough to force the equality of to force the logarithm law. So the general statement is if the system has superpolynomial decay in the sense said above, then the logarithm law and the local dimension exist at a certain target point, then you have the logarithm law. So this for each point where you can find the local dimension and almost each initial starting condition. So almost if the target point is good, almost each starting point will go near to the target following the law, the same scale behavior of the inverse of the measure of the small target in this sense. Okay, this when we obtained this result, of course one started to think about, but is this sharp? Why superpolynomial? We needed superpolynomial. The proof of this is like proving a strong Borel-Cantelli lemma for a certain sequence of targets, and it seems that this superpolynomial was important, but at first it was not obvious if this was a sharp assumption. After a while, we discovered with Sossol and Rousseau that indeed there are polynomially decaying systems for which the equality is not satisfied, and they are.
Just to have a heuristic understanding of the result, can you comment on this result and compare it with the geodesic flow you have discussed in the
I will come back to the geodesic flow because I will give a generalization of a kind of generalization of the Sarah-Levin result. But let me, since you asked what happened in the geodesic flow, it is proved that the geodesic flow is fastly mixing, is exponentially mixing. So it's a flow that satisfies, is even better than superpolynomial, is exponential. So you can apply, so it satisfies the main assumption, and so you can prove the logarithm law for the geodesic flow. And so what will happen is that if you consider how much time you need to enter in some given target, it will scale like the inverse of the measure. Is this does this answer your question? Or yeah, but of course these are quite general statements, but a particular case is that one. But I will come back to the geodesic flow in a few minutes. So let me just say that there are this superpolynomial is in some sense sharp because there are polynomially decaying systems for which the inequality is not satisfied. I have to say that these are skew products of a chaotic map and a translation with particular arithmetical properties. The only they are discontinuous. So these are systems which are discontinuous. But there are they are systems which are discontinuous, which have polynomial decay of correlation for Lipschitz and super polynomial decay of correlation for C infinite observable. But they do not satisfy this. Of course, they do not contradict the statement, because if you choose C infinite, is different from Lipschitz, and so on. There is also a, sorry.
For example, for arbitrarily large exponent for the polynomial, or not?
No, it's not arbitrary. This is not arbitrary. There are some bounds. I would, yes, about this question, maybe I would have to check, but I don't think we can have any polynomial, because we can compute we compute the rate of decay by arithmetical, so it's not a sharp estimation. I don't think we can say this. So, but this is an interesting question, because and then you can also find examples which are C infinity, and the inequality is violated, but they are less than polynomially mixing. I don't think I wanted to say something about this example, but I don't think I will have the time. Anyhow, let's go. Let me just say that in case you have a system which is polynomially decaying, you still can prove some bound. So you have not the equality, but the equality will be broken by a limited number, which can be computed in function of the local dimension and the exponent of the speed of mixing. But this is bounded. So let me, until now we talked about sequence of targets which are decreasing balls. And so you have a target point and you want to go near to the point. But, for example, for the geodesic flow, this kind of result is not enough, because in the geodesic flow, the real flow, so suppose you have a manifold, a surface, and then you want to consider the behavior of geodesic on the surface, and maybe you want to go near to a target point, but the real flow acts on a bigger manifold, which is the tangent bundle. So the real target of the real target that you want to hit is not a ball centered in this point, but a kind of cylinder in the tangent bundle. So it's already, when you want to think about geodesic flow, you are forced to suppose target sets which are not only balls. But this is not very difficult. The same result extends to family of targets which are sublevels of Lipschitz function. So you can consider a family of, you can consider a Lipschitz function, and the family of sublevels of this Lipschitz function and define the analogous of the local dimension, which will be again the limit of the ratio of the logarithm of the measure of the sublevel divided by the logarithm of the parameter which is relative to this sublevel. And if this limit exists, you call it kind of local conditional dimension, or what you want. You call it d mu of your function. If the system has superpolynomial decay of correlation as above, then you can prove the same thing. If the local dimension exists, then you have the logarithm of even in decreasing sequence of sublevel of Lipschitz functions. And let us see the corollary we can find for the geodesic flow. Now, let us consider a compact manifold with negative curvature, but this time variable negative curvature, because there were many results before for constant negative curvature, which are easier because in some sense there is an homogeneity of the space. Here we can consider a variable negative curvature, and since the flow is exponentially mixing, this is the hard part of the proof, because because the proving that the flow of the geodesic flow in this case is exponentially mixing it was an important result. But from this result we can get as a corollary that if we consider the problem I was stating here, how fast a typical geodesic go near to a given point, how near go to, you still have the logarithm law. Here the result is stated for the time one map of the flow, but you can do the same for the real flow. For the continuous time system is a slightly more complicated, but the results still hold in the same way. The only difference is that here you have d minus 1, because you have here you have discrete orbits. In the continuous time situation, you have a curve that is something that allows you to hit better your target, because it's from 0-dimensional, you have 1-dimensional thing. Anyhow, let me go to the application to Lorenz system. Well, the result, as you can figure, will be the same. Lorenz-like system satisfies a logarithm law. Now, I want to say we have proved this for a large class of what is called singular system having a singular hyperbolic attractor. But I will not introduce all the theory of singular hyperbolic attractor because there is no time, and this is quite complicated. I just want to say what are the main idea in this case, and what is the main feature of this Lorenz-like flow, and how we exploited this main feature to obtain first a decay of correlation result, which is not for the flow, is for a certain first nth return map on a certain section, and then from this it's not difficult to have the logarithm law on the section and then on the flow, because the return time is integrable. But let me say what kind of flow I want to consider. The main feature of this Lorenz-like flow is that there is indeed, in general, there can be many fixed points, but now let us consider simplest case. There is a flow where there is a fixed point, and the fixed point has two contracting directions and one expanding direction, and typical orbitals accumulate to this fixed point. So you can also, the simplest case where you can think about this is consider a linear vector field with a fixed point here, and this direction is contracting, this direction is contracting, and this direction is expanding. Consider a certain square here above the fixed point, and think about how it will be the trajectory of an orbit starting from the section. We'll do like this, and then think about that after going near to the fixed point, let's say we choose a certain neighborhood of the fixed point, and in this three-dimensional figure, and there will be an ingoing section, which is this one, an outgoing section for the flow, which is this one. So the orbit will start from here, go here. Then let us suppose there are no fixed point anymore in the space, and remaining part of the dynamic is in some sense hyperbolic, and the remaining part of the dynamic will bring back the orbit, typical orbit, again on the ingoing section, and so again near to the fixed point, and so on, going sometime here, sometime there, and altogether this makes a Lorenz-like flow. This, if you remember the picture of the attractor of the Lorenz attractor is made like this. There are the two wings of the butterfly, and in between there is this fixed point which accumulates the orbit, and sometimes you go on one wing and sometimes you go on the other wing. The mathematical theory of this kind of flow arrived very late in some sense, and the tool that were successful to give rigorous result of this kind of flow were to consider a certain section and to consider the return map and to understand which are the properties of the return map, and from the properties of this return map to obtain results that then are lifted to the flow. And which are the properties of this return map? The main properties are that there is a foliation which is preserved, because you see near to the critical point, even if this is linear, but yeah, I forgot to say, you can build a simple model of the Lorenz flow taking just a linear fixed point here and then a flow that brings back the orbit again near to the fixed point. This is called kind of geometrical Lorenz model, but the real Lorenz system has a non-linear flow around in the neighborhood of the fixed point, which gives more complication. But more or less, qualitatively, the picture is the same. And what you want to do is the same as you do for the linear one. And what happened is something similar to this case. So you see, in this case, if you consider this vertical leaf is sent to a small segment here on the exit section, then it will go again here, and so you can suppose that there is a foliation which is preserved by the dynamic on the return map, and that the leaves are contracted. If you how much time I have? Maybe I yeah. So there are questions until now, because it seems to me that I will be maybe a little bit. I don't know if I'm going fast or saying something that everybody knows, but anyhow, if there are questions, please stop me. So now, what I said until now about the Lorenz system is that the Lorenz system is made qualitatively in that way, and the tool to study it is to choose a section and then understand which are the properties of the return map on the section. And let us now discuss a little bit more, let's say, qualitatively this feature of the return map on the section. Here in this picture you see a square section and a kind of picture of the return map. What is the meaning of these two cusps? If you consider this half square in the return map on the section, the image of this half square will be this cusp. What happens is that this half square is contracted in the vertical direction, because there is this strong contracting direction, and it's stretched in the horizontal direction. And here is also stretched quite a lot because there is an infinite derivative here. There is a cusp because there is an infinite stretching here. And the other half of the square will go into this other cusp. And it will do this in a way that a vertical segment is sent again to a vertical segment. Of course, in the real Lorenz system, this is, let's say, the linear model. But in the real Lorenz system, what can be proved is difficult, but it can be proved that you can choose a certain section and a certain return map, and such that after a change of coordinates, you have the same situation. But this is the simplest case where I can describe the main feature of the map. But these are the good features, because the good feature is the contracting foliation. The bad feature is that there is no obvious Markov partition or Markov, let's say, situation, and there are unbounded derivatives, what we do now is to, okay, we understand what are the main features of the real Lorenz system. Now we forget it and we say, let us consider a map doing the same thing of what happened in the Lorenz system, and then we axiomatically start from a list of assumptions and prove a certain theorem that will be again applied to the Lorenz flow. So let us consider a map like this. So let us consider this. Sigma is the square. Let us consider a map from the square to itself such that the map is a skew product. This is because there is a foliation which is preserved. The vertical foliation is preserved, so where the x coordinate will go only depend on x. So the dynamics will be seen like a skew product of a one-dimensional map and a two-dimensional second coordinate, which has important properties. The first property is that the leaves are contracted. Then there is a regularity property which is a kind of bounded behavior of G with respect, is a kind of Lipschitz mixed situation. G must when you increase the first coordinate in G, the increasing of the value will be bounded by a constant time the difference. So it will mean that your system cannot, how to say, bend too much your a starting set to its image. This condition is true in the geometric Lorenz. In the real Lorenz must be changed a little bit. Well, it can be relaxed to something which looks like bounded variation. This looks like Lipschitz, but it can be done with something like bounded variation. I don't want to define because if not, it's too technical. Then there is the uniform contraction, and then the properties of the one-dimensional map, which is induced by the fact that the vertical foliation is preserved. And this one-dimensional map is a piecewise expanding map with with infinite derivatives. So let me just draw in a real situation. The one-dimensional map is made like more or less like this. Is expanding, but piecewise expanding with some infinite derivative at some point. Of course, for piecewise expanding map, we know many things. We can prove decay of exponential decay of correlation. Even if, let me just mention this, is piecewise expanding, but the regularity we can suppose for the derivative is quite low, but there is already a theory that can allow to handle this low regularity. So now we want to understand the decay of correlation of this two-dimensional map, of a two-dimensional map having all these features. The idea, the result is that this two-dimensional map, which is made like this, has exponential decay of correlation with respect to Lipschitz, even with respect to some more general norms which are anisotropic, but for the moment let me say Lipschitz, and this induces a logarithm law for the flow. Now let me finish by trying to explain which is the main idea in the proof of the decay of correlation, which is a kind of I think is an argument which is between coupling and anisotropic norms. Is a little bit homemade, but I would like only to there are many technical points I will not talk about, but I want to say the idea, which is very simple, I think. The idea is the following. We want to, well, the map is something like how the map works. On one coordinate you have piecewise expanding, so the pieces are stretched, and on the x direction you have just a piecewise expanding map. On the other coordinate you have uniform strong contraction. So when you want to look at decay of correlation like things, after all what you want to look is something like this. There will be an invariant SRB measure, which will be in this case a fractal because there are contracting direction. And suppose you start with a certain measure and you want to see how fast the starting measure converge to the invariant measure. The idea is that you take this measure, let me say like a measure supported here. What happens? If you iterate and project this measure at each iteration on the base, what you see is the piecewise expanding one-dimensional map. So on one, for the projection, you see that everything is mixed, and you will see an exponential convergence to the limit. On the other direction, you have contraction. So the idea is to decouple, since this is a skew product, try to decouple these two behaviors. And how to do it? Since if you want to see how fast this measure converges to the invariant one, maybe you can estimate the distance in a way that it takes account of this skew product situation. And what you do? You take your measure and the iterate of your measure, and you disintegrate the measure into one measure on the base, which will be the marginal of this measure, and a family of probability measure on the leaves. Why this is interesting? Because then you have the projection on the invariant measure, which is another measure here, the projection of your starting measure, and one converges exponentially fast to the projection of the invariant one. On the leaves, what you have? On the leaves, you have contraction. So even on the leaf, you will have something that is contracted, and it will help you to converge. So I tried to explain the idea. Let me go a little bit more into detail. So what we do, what you need to do is to estimate the distance between two measures as a function of the distance of their projection and some distance on the leaf. The distance of the leaf will be contracted by the contraction, and the distance of the projection will be contracted by the expansion. But of course, you need two different norms to have the contraction, and that's why these are we have two different definitions. So, given two measure on the square, but let's say, given two measure, let us consider the Wasserstein distance, which is this. You test the two measure against all the Lipschitz function with Lipschitz constant 1, and consider the total variation distance. Now we will consider the Wasserstein distance on the leaf and the total variation distance on the projection, because we have a convergence for these two with our if the system satisfies the assumption we have now. And then let us define this kind of anisotropic Lipschitz norm for an observable, which is G is a function. The norm of G is the infinite norm for G plus the biggest Lipschitz constant you see going in the vertical direction. So you don't care about horizontal variation of G, but you care that the vertical variation of G should be Lipschitz. And you define this kind of anisotropic norm of G. Why I gave this definition? Because you can prove the following, which is quite easy. If you have two measures on the square and you disintegrate the two measures into a family of measures on the leaves, gamma is a leaf, and a marginal, and you suppose that the average Wasserstein distance of the leaf is smaller than epsilon, and the total variation distance of the marginals is less than delta. Then, if you take a certain observable and you test the two measures on this observable, this difference is bounded by the anisotropic norm of the observable times the sum of the average distance of Wasserstein on the leaf and the total variation on the base. Why I do this? Because now, if you remember the idea, now the leaves are contracted. The Wasserstein will decrease in the same way. The Wasserstein distance, if you take two measures and you contract the space, their Wasserstein distance will go in the same, with the same rate of contraction. And this other distance will decrease because of the one-dimensional maps, which has decay of correlation. So, well, I think I'm almost done with the time. I think I'm happy because I think I said the main idea. Then you have to feel it in all the technical detail. The first detail is that if you do like this, you start with it's easy to prove that if you start with something which is absolutely continuous with Lebesgue, then it converges exponentially fast to the invariant measure. But it's not exactly what you want, because if you do like this, you prove that you can bound this integral, where here and here you have the Lebesgue measure. But to prove the decay of correlation statement is slightly different. Here you have mu, and here you have mu. But the first step is to do like this. You prove, you bound this integral. We call it convergence to equilibrium. I don't know if this is standard in the literature. If you iterate the Lebesgue measure or something, we call it convergence to equilibrium, while if you iterate something which is already absolutely continuous with respect to the invariant measure, so it's a fractal, we call it decay of correlation. This is and then we will connect the two things. But if you do like, if you consider now this convergence to equilibrium, it is, and you define, you have a certain function f on the interval. No, sorry. If you have a certain function of the square, you define the projection of the function as the average over the vertical leaf. This is just a notation to state the theorem. The theorem is like this. If you have now our function with which works like I was saying before. So is a function which is a skew product, two-dimensional function which is a skew product, but the first coordinate has exponential convergence to equilibrium with respect to observable in L infinite and some norm some norm. This is general. This T must be a little bit regular in this way. It must have some a finite number of continuous branches, and the leaves are contracted. Then the two-dimensional map, for the two-dimensional map, you can bound this integral of convergence to equilibrium as an exponential times this anisotropic Lipschitz norm for this observable, and this norm, which is the norm for which you have this exponential convergence to equilibrium for the one-dimensional map, plus the L1 norm of F. This is, I put L1 here because maybe this could be weaker than L1, even if I don't know any example of this. Maybe it's not even not possible, but for the moment, in our case, here there is a BV norm. So this is the general tool we use to decouple, to obtain from a one-dimensional convergence to equilibrium and contracting leaves a two-dimensional convergence to equilibrium. Now let me, so of course there is something to apply it on the real map, but it can be done. And in here the main thing is to have from this estimation, which is the convergence to equilibrium, an estimation for the decay of correlation, which is this one. And but hopefully the two things can be related, providing you can estimate these norms. So what happened? I will not give the final a precise statement, but starting from these two norms for the observable, you can change it a little bit and satisfy this assumption and obtain a decay of correlation result for the nth return map of a singular hyperbolic flow. And well, to explain everything will take much more time, but I wanted just to say that the main idea which allowed us to arrive there. And well, I think I finished my time. So thanks, and I will skip the last part, which are the negative, some more explanation on the negative result, but let me go just to a list of reference if you are interested in seeing the details. And thank you.
So the last result about convergence to equilibrium and decay of correlation is completely general results, right?
Yeah, this was after a suggestion of Carlangelo, because yes, but it's very simple. I can. It's just add and subtract. The idea behind, intuitive idea behind, is like the difference is that here you start with Lebesgue, more or less, and here you have the limit of the iterate of Lebesgue. So it's like you iterate a certain number of time, and you take account of what happened, and then you.
So it's remarkable that nobody did it before, right?
But for Carlangelo was simple. I asked him, is it possible to, but
and the other direction is trivial, or it's wrong? Or?
I don't know. Indeed, we discussed with him with this, and what's not very clear. But I think nobody tried to really go into detail in this.
So sorry, did you understand my question?
The other direction. Yeah. So from decay of correlation to convergence to equilibrium.
So what's your answer?
My answer is that it seems we did not really worked on to see if how difficult it is, but we don't know. We don't know. I was saying it's surprising that it seems that in general people never really tried to make this general.
Oh, I remember that Dyson Young asked me this question in 10 years ago. And at the time I didn't know how to answer,
but this is simple.
More
From this
yeah.
to this is simple. It's half-page proof. And the converse I did not really try, but
Doesn't seem to be the case. Well, thanks a lot.
thank you.